This lecture will largely be a continuation of what I talked about on Sunday. Let me begin for the first few minutes by just sort of reminding you what we did last time. So the goal was to ask how do we go from the unitary dissipationless Schrödinger equation, and there's no sound. Do you want me to just talk louder? Or? Okay. So how do we go from this dissipationless and unitary Schrödinger equation, and how do we go to hydrodynamic equations of motion? So classical but nonlinear and stochastic in general. And in particular, the equation that we wanted to understand was the origin of a nonlinear diffusion equation with some random noise obeying the fluctuation dissipation theorem. Okay. And so the setup that we started with was that we said, well, let's consider a many-body quantum system. Here I'm just drawing something in 1D, but we can do it in any dimension. And we're going to sort of divide up the system into different bins. And we'll assume that we have a local Hamiltonian such that the Hamiltonian is a sum of terms which act within each of our regions. And then there will be some small boundary term. And all of these h of x commute with one another because they act on different Hilbert spaces. And so we conclude that there will be some slow dynamics associated with essentially energy eigenstates in each region sort of interacting with each other via these small boundary terms. Okay. We defined a Hilbert space for each of these h of x, from which we can build up our global Hilbert space in a straightforward way. And then the idea was that we said, well, you know, this many-body wave function contains a lot of information, but we don't really care about all of the information in the many-body wave function. All we really care about is the probability that we measure the energy h of x in each region separately. We only care about the probability that we measure that energy in each region, you know, to some accuracy delta. So for each E of x, it has some, you know, many-body spectrum with exponentially small energy spacings, and we said, well, let's you know, group them together into bins of size delta. And we just want to ask what is the probability of finding the many-body system to have energy E in every region. So this vector E just corresponds to a vector that contains information about how much energy is in all of my regions. Okay, and then we introduced this memory matrix formalism that allowed us to obtain an equation for this probability by starting with the Schrödinger equation and integrating out many of the degrees of freedom in the Schrödinger equation. And the final answer that we arrived at was that in a sort of general non-integrable quantum system on sufficiently long timescales, this probability obeys a Markov equation. Okay. So at this step, we've already introduced dissipation into the problem, and where that dissipation is coming from is, loosely speaking, the fact that your sort of many-body density matrix is decohering in off-diagonal sectors because of these surface terms. Okay. So let me just remind you of the last equation that we had last time. Minus And these transition rates W, at least with some further assumptions, they're symmetric and they're given by Fermi's golden rule. Okay, so some of and then this dynamics is energy conserving, and so there's a delta function that enforces that any energy that's energy can only be exchanged in equal amounts between different boxes. Okay, so that was where we left off last time, and now we just want to continue by analyzing this equation and putting it in a much simpler form where it will become easy to see where the hydrodynamic equations come from. Okay. So first, let's just take the continuum limit in these E's, and I'll explain why this is sensible to do momentarily, but in practice what we're going to do is just replace this sum with an integral over all of the possible energies that we could measure in each region. And with this approximation, our Markov equation just becomes the following. Okay. Now, at the moment, this equation is not very useful because it's a non-local equation in this energy space. But now we want to make the key observation that if you look at this set of allowed transition rates, all of the transitions that are allowed in this system are extremely special. Okay? So if we ask how can we exchange energy between different regions of space, we find that transitions are forbidden unless E and E prime are very similar. Okay? So the energy that's contained in every region will have to be almost the same before and after the transition. The only thing that can happen is something like the following. So suppose I specify for you the energy that I have in every region before, and now after I undergo one of these transitions, the only thing that I'm allowed to have happen is for some small amount of energy, epsilon, to be exchanged between two adjacent regions. Okay?
Why is it small? If you have hopping between these.
So that's the next step. Okay. So now you could ask, okay, so just if you look at h of x and y, you might say, well, this epsilon might be all the way up to L to the d minus 1, because that's the norm of the surface Hamiltonian. But the key point is that this h of x and y is not some sort of horrible non-local beast, right? It's a sum of a bunch of local terms. So just to be schematic, we have a bunch of few site terms. And these few site terms will proliferate all across the surface. But in any given term, we only act on a few sites. Okay? And so now you can ask what happens when I act with h of x and y on a state alpha. And essentially what happens is that h of x and y acting on alpha will give you a sum of L to the d minus 1 terms. In each one of those terms, you will have, well, let's just say E alpha of x going to, well, let's just say E of x will go to E of x plus epsilon, where this epsilon is actually independent of the system, or of the region size. Okay, and then there will be some coefficient sitting in front. But the key point at the end of the day is that this is not the correct scaling. The amount of energy that you can exchange in in this process is independent of L. Okay, so what have we learned? Well, we've learned that we exchange small amounts of energy at any given time, and we only exchange energy between adjacent boxes. And so now let's take this equation and simplify it, okay, using what we've just found. Okay, so the first thing to observe is that let me define epsilon, the vector, to just be E prime minus E. This is very small compared to E and E prime in some sensible component-wise sense, because all of these components scale extensively in the system size. And so with that in mind, we can go to our Markov process and start Taylor expanding in the energy exchange. Okay? So as an example, we can take P of E prime over omega of E prime minus P of E over omega of E. To first order, there will be some linear correction coming from epsilon. There's a second order term that will be important, but it's sort of straightforward. I won't write it down. And then these transition rates are also very sharply peaked because of this result. Okay? So keeping that result in mind, the transition rates W of E and E prime, we can think of these as, just to be schematic, we can Taylor expand this function in terms of epsilon. Note that this function is symmetric, so that will simplify the terms that I'm allowed to write down. And W2 and then there will be some function of support only on epsilon independent of L. Okay, so now we can take this Taylor expansion and this almost Taylor expansion. We can plug it into our Markov equation, and we arrive at the following, now no longer a non-local equation, but now a differential equation. So I'll just skip a few steps here. X, Y. And these rates sigma can be calculated explicitly. So these are, okay. So our boxes exchange energy with one another in this sort of diffusive pattern in this very high dimensional space of all possible energies that we can measure in all regions of space. The transition rates are roughly given by the fluctuations in energy. Okay. And now we're almost to the hydrodynamic equations. So okay, so at this point, let me just define this sigma. I'll divide it by omega and call the result. The board is scratched here. Curly D. Okay, and with this definition, my equation takes the following form, which will start to look nice. Okay. Okay, so we get some linear term in derivatives epsilon. This is sort of a transport term. And then we get a diffusive term okay. And yes, let me just comment for the moment that there will be some subleading corrections in spatial gradients. Where these are coming from is essentially that we only, this equation has higher derivative corrections that we've dropped. Yeah?
Do you always take the number of boxes to be smaller than the size of each box?
No. The limit, ideally, the number of boxes goes to infinity faster than the size of each box. Yeah?
Can you explain again what's the validity of this Taylor expansion? You're absolutely smaller than what?
Yeah, okay, so let me just make a few extra comments on this. So the epsilon is independent of the system size, and the average energy in each region will be extensive. And so the basic idea is that when you look at this function, you'll be Taylor expanding in this parameter, epsilon dE. And this will scale as L to the minus d. So to add sort of higher derivative corrections to this equation, they're effectively going to be suppressed on any physical solution by this coefficient.
Why does it scale like that?
Oh, because, well, okay, so the average energies that we're thinking about are extensive. And
In the box.
yes. Yeah, and so the point is, if we're thinking about sort of smooth distribution functions in P of E, in fact, yeah, there will always be fluctuations that diverge with L in E, and that will be something that we'll see in a bit. Okay. In any event, so we have this scaling, and so there will be some corrections to this diffusion equation, but they'll be small. Okay, so now at this point, where we're going to go is as follows. I won't sort of detail all of the steps here, but the basic idea is that we can call this a Fokker-Planck equation. Okay, and what is the Fokker-Planck equation in general? Well, we're asking about the probability that we measure some energy in some region of space, and we're interested in the joint probability for all regions all at once. Now, it's equivalent mathematically to define essentially random variables E of x. So these E of x will not be deterministic. They'll obey some fluctuating equation. And you can take this Fokker-Planck equation and you can exactly rewrite it in the following form. There's some slight subtlety I won't talk about, but it's sort of a negligible issue. D of E x y. All right, I'll define this beta momentarily. There's a random noise term, and this random noise term is Gaussian, and it has the following fluctuations. Okay, now what is this beta? Well, it's just going to correspond to the inverse temperature of my system, and I can define that as follows. So recall that this factor of omega corresponded to counting the number of eigenstates within each of my bins. And just using some elementary thermodynamic identities, we obtain that this derivative is equal to the derivative of the entropy with respect to energy in each region. And this is more commonly known as 1 over temperature. Okay.
When you chose this number, you did it without any intuition. You just chose a bin, some size, independent or maybe dependent, but without any intuition on where it is in the spectrum. Is this true?
Chose what?
When you chose the number of energy eigenstates in each bin, in each energy state, you made no assumption.
Well, generally the number of eigenstates will be exponentially large in the volume.
But how did the dependence of S on E, there was no physical intuition there.
Oh, I mean, look, this is just sort of thermodynamic state counting. So for each h of x, you just calculate, how many eigenstates there are in any given energy window. And you can define a function s whose logarithm, you can define a function s for which the number of states, within a given bin is e to the s. And that's all we're doing. So there's no assumption here. I mean, these are just thermodynamic definitions. Okay. All right. So now we're almost there in saying that this is our diffusion equation. Okay. So let's try to take the continuum limit of this equation. So we don't want to talk about fluctuations on, between neighboring boxes. We want to talk about long wavelength fluctuations over many boxes, over many regions. And so this transition rate, curly d, okay, you'll just have to trust me that this is sensible, but in the long wavelength limit, you can approximate it as being given by the average value of the energy times the function lambda of x and y plus order 1 over L. This lambda of x and y essentially corresponds to the following matrix. It's essentially a discretized Laplacian, as we'll show momentarily, but it's going to be equal to the number of neighbors of x if x equals y. If x is not equal to y, but x and y are adjacent, you get -1. Okay. And you can understand fairly easily that this is the, in the continuum limit, this looks like the Laplacian. So if I take the sum x and y, lambda x and y, f of x, g of y, this becomes essentially an integral over x of times L squared. This overall factor of L squared is just coming from the fact that there's no L in this equation. But we don't want to use microscopic, or we don't want to use coordinates where L is set to 1. Okay. All right, so with this in mind, we can take this stochastic equation and rewrite it in the continuum limit as follows. So dt of E of x, this is minus the divergence of our transition rate as a function of E, L squared times the gradient of inverse temperature plus the noise, which obeys the same variance. And let me just write this in the form of a conventional diffusion equation by going from beta back to E. So just using some thermodynamic identities, the gradient of beta is minus beta squared over specific heat times the gradient of E. And so we arrive at our diffusion equation, del dot dE and the diffusion constant is given by d L squared beta squared over C. Okay, so at this point, we're almost done. So this is it's a nonlinear diffusion equation that has random noise. So now what we should check is that our noise obeys the fluctuation dissipation theorem. So typically when people talk about this sort of fluctuating hydrodynamics, the fluctuation dissipation theorem is a microscopic constraint that you would have to impose by hand. Okay? But from this perspective, it's not imposed by hand. It will pop out immediately. Okay? All right. So, well, okay, I guess I already wrote the, where is it? Oh, yeah, here. Okay, so this is the variance of our noise. And let me just, using this definition of energy diffusion, let me just rewrite this equation a little bit. So this is going to be 2 times temperature. This is, of course, just 1 over beta. There's a factor of temperature times specific heat. This is essentially a thermodynamic rescaling because we have an energy here. And then the final term in the continuum limit is just the Laplacian acting on a delta function. And well, you may recognize this as the ordinary fluctuation dissipation theorem from stochastic hydro. And here, you know, it's coming immediately from the Fokker-Planck equation. Okay? All right. Let me state one more time that as we discussed before, the non-Gaussian corrections to the noise spectrum are really suppressed in gradients. Okay? So, you know, you really honestly do have, to leading order and derivatives, Gaussian fluctuations. There are some high-energy theorists that are working on building effective field theories for hydrodynamics, and this is essentially a microscopic constraint on those effective theories. Okay. All right. So that's the answer. This is hydrodynamics contained in the Schrödinger equation. Let me just sort of quickly recap the punchline. So the punchline is that we can start from a many-body density matrix. We can think about asking, what's the probability of measuring eigenvalues for the local, energy density effectively, but eigenvalues of local Hamiltonians to be a given value. We can ask how this evolves as a function of time. In a chaotic system, this will evolve according to a dissipative Markov equation, which reduces to this. Okay. All right. So for the rest of the lecture, we'll see how much we get to. But I thought I would address the following questions, which maybe they're obvious to you, but at least to me they were not so obvious. So, okay, one question that you might ask is, how do we know for sure that energy is the only slow degree of freedom? So, sort of, implicit in this equation, it seems as though h of x is the only slow degree of freedom. Now we can partially address that. We can ask why is, as an example, h of x squared not slow, or as we'll see more accurately, why is this not independent? Okay. So I'll show you just from the Fokker-Planck equation that we really, we have track of a lot more than just the average energy in each region, and we can really honestly say that there is no new degree of freedom contained in essentially higher moments of the energy distribution function. Okay? So there's only one hydrodynamic degree of freedom corresponding to average energy. Okay. The next question that we would like to ask is, or really, I guess the next thing that we'd like to show is the emergence of a local temperature. Okay. So typically, the sort of canonical law in statistical mechanics is that temperature is strictly only well-defined in equilibrium. Once you go out of equilibrium, it's not well-defined to talk about a temperature because there are essentially fluid frame choices. What I will show is that there's a sort of natural frame choice where there's a sensibly defined local temperature, and correspondingly there's essentially a special choice of density matrix for the many-body wave function that evolves in a very simple way. Okay? So we'll see in particular that local thermal density matrices are a special class of quantum mixed state. They have particularly simple time evolution. Okay. And the last thing, which we may get to, is the emergence of a local second law of thermodynamics. So recall that if you have a unitary quantum mechanical time evolution equation, there is no entropy production. But part of the standard law of hydrodynamics is compatibility with the local second law of thermodynamics. So you might ask, sort of from this perspective, where is this entropy coming from? And so there's actually a very simple answer to that. Okay. But we'll start with this question, okay? So the first thing that will be helpful to do is to go back to this equation here and ask, can we classify sort of in an easy way all of the steady states in our system? So the idea is that we want to talk about slow degrees of freedom. It would be easiest to do that if we identified some steady state and then weakly perturbed it and asked about how the resulting fluctuation relaxes. Okay? So it turns out that it's very simple to identify the steady state solutions of the Fokker-Planck equation. To do that, observe the following. So if you have something like this, okay, then because of these transition rates having this factor of lambda, this is roughly going to be d, and then there will be a relative derivative with respect to the energies in adjacent boxes. And what this means is that the following class of solutions exist. So we have a factor of density of states, and then we can multiply by an arbitrary function of the total energy. Okay. Now you may recognize this equivalently as the statement that essentially arbitrary superpositions of microcanonical distributions solve the Fokker-Planck equation. Okay. All right. Now, a particularly useful choice of this function will be f of E total is e to the minus beta E total. Now, beta, will of course correspond to a sort of global inverse temperature that the system is nearby, but for the moment it's just an arbitrary parameter. Okay. And we'll see, as we go through the lecture, why these kinds of density matrices are so nice. Okay. Okay. So first, let's just talk a little bit more about what our equilibrium distribution looks like. So using that the density of states omega is just a product of e to the s in each region, we can rewrite our equilibrium distribution as a separable product of the local entropy in each region times beta of E of x, and then divide by some partition function. Now, equivalently, if you have a smooth function s, this will be, to very good approximation, at least for E that aren't too large or small, this will be approximately Gaussian. Okay? E bar beta. The variance in this Gaussian distribution is given by minus dE d beta, which is alternatively temperature times the specific heat in each region. And let me emphasize that this scales extensively, and what this means is that energy fluctuations in this canonical distribution will be L to the d over 2, as is well known in StatMech. Okay? All right. So with this in mind, we want to talk about fluctuations around this equilibrium distribution. So it will be useful to define a normalized energy, eta of x. And what this eta will do is just subtract off the average value of energy and normalize by sigma, so this Gaussian becomes e to the minus eta squared over 2. Okay. Okay, so now we want to solve the Fokker-Planck equation and ask about what the fluctuations of this Fokker-Planck equation do, what they look like. And it's useful to analyze the Fokker-Planck equation in a clever basis. Okay? We have a linear equation of motion, and as we'll see, it's sort of useful to sort of guess in some sense what modes will relax among themselves. And to do that, I claim that there will be a natural family of states to consider. They'll be parameterized by a vector of non-negative integers. So this n of x is non-negative. And these special distributions will be the canonical distribution times products of Hermite polynomials. Okay. Now, these Hermite polynomials you may remember from the quantum harmonic oscillator. And for the same reason that they show up when you diagonalize the quantum oscillator, these same functions will show up here. Okay? In particular, I want to define a useful inner product to essentially simplify my Fokker-Planck equation. Okay, so maybe hopefully these steps, if they're a bit mysterious now, hopefully in a few minutes it will make sense. So the square bracket here means that this is an inner product on this classical space of probability distributions. And I'm going to weight by the canonical distribution f beta g of eta. And if I normalize my Hermite polynomials suitably, I found an orthonormal basis for the Fokker-Planck equation. Okay. Okay. So now I can think of, I had this equation for P of E and T, but if I work by expanding my probability, so I want to take P of E, and I want to write it as a sum of some coefficients times these P n's. I can think of that as P going to a sum over Cn of n. And in this language, the Cn of t's obey a sort of simple differential equation. Okay, this k of n and m is just going to be n okay. And, well, okay, apologies, there's maybe not the most elegant looking formula right away, but let me just sort of explicitly evaluate this out. We'll see shortly that the dynamics is actually not very complicated. Okay, so n km is going to be d over sigma squared, the sum over all adjacent regions. Now, in each region, or for each h of x and y, the only thing that can change are the excitation numbers n of x and n of y. So, okay, so I have this sort of overall prefactor, and then, yeah, there's just a sort of annoying formula, but what you'll notice about this formula when I'm done writing it is that the transitions that are allowed are extremely restrictive. So you can either not transition at all, okay, or you can exchange a single quantum, or you can exchange a single excitation. Quantum is maybe not the best word here because this is not a quantum mechanical system at this point. +1. Okay, and then there's a sort of complex conjugate term that I won't write down. Okay, so what's the punchline? So we have this basis we're analyzing the Fokker-Planck equation in, and in this basis, excitations can hop between adjacent sites, and that's all that happens. Okay, so it's particularly simple. Okay. Okay, so now the key observation that's sort of immediate from this formula is that transitions n km can only be non-zero if, so only if the sum of excitations is unchanged before and after the transition. Okay? And this is not, so you may sort of think that, okay, I've found for you this huge number of accidental conservation laws. Is that inconsistent with hydrodynamics? And actually, this is sort of totally mundane. What this corresponds to is the following simple observation. So the conservation of the sum over x of n of x, this basically corresponds to the fact that you'll recall that I could find a steady state for a very broad class of functions. One class of function that I could consider is the following. So I could take 1, I could add to it some A1 times the total energy, A2 total energy squared, so on and so on. The coefficients A1 and A2 correspond to the number, the weight, if you will, in basis vectors that have a given number of excitations. So this is really simply encoding conservation of energy, but the point is that there are a very large number of steady states. Okay. All right. So with that said, let's start thinking about what the dynamics actually looks like. So the first thing we can do is we can look at what happens if I have a single excitation. Okay. If I have a single excitation, then it's useful for me to just, these are the kinds of vectors that I'm allowed to look at. So if the excitation lives on site x, I can just call that vector x. Okay. And you can show easily from this formula that x, k, y is d over sigma squared lambda of x and y. Okay, now physically, what are we trying to get at? Well, it turns out that x, what this inner product effectively corresponds to is the expected value of the operator h of x in my many-body state. Okay. And just for ease of notation, I'll write this as average h of x. Using this transition rate, I find a essentially linearized diffusion equation for this single excitation. The energy diffusion constant is really the correct one if you go and, well, I've erased it by now, but if you look at what the formula for the energy diffusion constant was, it actually is correctly reproduced. Okay, so that's what happens if we have one excitation. Okay, so next we can look at what happens if we have two excitations. Okay. So in this case, let me just draw for you a picture. Okay. So each of these dots will correspond to a site on which one excitation lives. Then I will have some other dots corresponding to the site where the other excitation lives. And I can parameterize my, my allowed space of configurations for these two excitations by essentially doubling, in some sense, my lattice to this simplex. Okay. So for one dimension, I can think about the dynamics as not the dynamics of two individual excitations. I can think of it as the dynamics of a sort of single excitation, but on this higher dimensional space. And if you look at these transition rates, what you see is that unless the excitations are very close to one another, okay, this transition rate is completely independent of the existence of the second excitation. So everywhere over here, essentially the diffusion for this excitation and this one are completely decoupled. Okay. So now what do these n equals 2 excitations correspond to? Effectively what we're trying to measure is h of x, h of y, subtract off their average values. But we're trying to measure this kind of a correlation function. We put in two excitations. We evolve it forward in time. And the punchline is that on long length scales, we arrive at the following equation. So this correlation function of two excitations, h of x and h of y, actually contains no physics beyond the single excitation sector. Okay? So actually everything that we would care about if we have two excitations, we already know from our theory of a single excitation. Okay? This would often go by the name of cluster decomposition. Okay? And the idea is that this is not really a new interesting degree of freedom. It's just the product of two elementary excitations. In the same way that when you do kinetic theory, you typically say that if I care about the information contained in two particles, that's generally just a product of the information about each particle separately. This is sort of an analogous statement. Okay? So there's really no additional information contained in any of these higher sectors. Okay? And so what we conclude is that this is not an independent degree of freedom. Okay? So the only sort of honest degree of freedom in the theory is the single excitation. Essentially, the energy density itself is a hydrodynamic excitation. Higher polynomials in energy density are not independent. Okay? So there's one degree of freedom in this hydrodynamic limit. Okay. So that answers the first question that we had. What we now see is that, sort of the more complicated functions of h of x that we consider, all that will happen to them is that they will essentially split up into independent random walkers, and those sort of diffusive excitations will move around independently of anything else in the system. Okay, so this is all sort of fairly close to equilibrium, and so now we might ask, can we try to start looking at sort of more complicated fluctuations? Can we start looking at essentially nonlinear diffusion dynamics? Okay. And in particular, what we'll see is that there's a sort of natural family of solutions to the Fokker-Planck equation that has a simple time evolution. So yeah.
This result, can you think about that as some sort of central limit theorem? So you have a very narrow distribution, so it's almost like a delta function. So basically the first moment gives you everything. So the fact that the bins are large.
So, I mean, part of this is coming from the fact that the bins are large. That's certainly true. But I think I would also just comment that this is the statement that at finite temperature, you're not generally going to have sort of long-range correlated excitation. Like, the correlations that are sort of present at the initial time will be maintained. But you're not going to get anything more complicated than that. Okay. So now the next question is, can we understand the extent to which a local temperature is naturally defined, and in particular, can we understand the sort of the naturalness of the thermal density matrix? So, for this discussion so far, I've just essentially said, well, let me, for whatever reason, just tell you that I'm going to think about dynamics around this canonical distribution. But you might have asked, why did I make that choice? So what we'll see is that the dynamics of these kinds of states is particularly simple. Okay. All right. Let me sort of start with a broader claim, and then I'll partially justify it for you in a simple limit. So suppose that I want to look at I claim that the following kinds of distributions are very natural. Okay. So E, this is just my ordinary density of states. So suppose that I gave you, at time t equals 0, this distribution function, which was a product of essentially decoupled distributions on every site. In the quantum language, this would be the statement that the density matrix was a tensor product of local thermal density matrices. Okay. And now the claim is that these distribution functions are the unique distribution functions that maintain their simple form over time. Okay? So essentially, these are the unique distributions that don't start generating long-range classical correlations at late times. And I'll show you perhaps what that means. Okay. In particular, there's a sense in which the time evolution of this state is just given by partial t of beta is just the diffusion equation. So these local thermal density matrices obey this really simple equation of motion. They don't grow more complicated over time. And the inverse temperature will just diffuse to equilibrium. Okay. So to do this, let me sort of first consider the regime where fluctuations in beta are sort of relatively small. Okay, so I'm sort of fairly close to to my canonical density matrix. And so if fluctuations in beta of x are small, then you can think about the following happening. So P of E is approximately going to be a product over every region, e to the minus E of x minus E average energy minus sigma. And this essentially corresponds to a small change in the temperature, but I've denoted it in this way. Okay, so effectively the temperature beta of x is just going to be beta, and I think in this notation it's minus ax over sigma. And now we can ask, how do these states evolve with time? Okay. And okay, let me just sort of state that with a little bit of work, let me just define one more thing for you. So in the Hermite basis, these states actually take a very nice form that you may recognize. So these are essentially the analog of classical, or of coherent states, of the quantum oscillator. Okay. So these states evolve in a very simple way under time evolution. In particular, the time derivative of A is given by the sum of x adjacent to y of d naught over sigma squared lambda xy d dA of x minus d dA of y, a of x minus a of y, a. Now, what this equation tells you is that this coherent state will remain coherent for all times. The only thing that happens as I evolve with time is that the coherent state parameters themselves actually change. Okay? And in fact, what will happen is the coherent state parameters will just diffuse back to equilibrium. Okay? So in the long wavelength limit, I arrive at this equation. Okay? Now, it's a bit more work to get to this nonlinear equation, but you can argue this with a bit more care. Okay. Now, the other point that I want to emphasize is then what happens if you didn't start with one of these simple locally thermal density matrices. So what would effectively happen is that I start with, let's say, rho of x is some tensor product of some complicated function of the Hamiltonian on every site. If it's not exponential, what will happen is this state will evolve into some horrific mixture of these kinds of local thermal density matrices. Okay. So you'll get something that looks kind of like this. And this P of beta will be extremely complicated in general. And this will effectively correspond to sort of, in some sense, almost classical entanglement between very different regions, or between distant regions. Okay. All right. So in the last few minutes, let me sort of answer the last question, which was, where is the local second law of thermodynamics coming from? Okay. So recall that if you take the Schrödinger equation, and now you ask about the time evolution of the von Neumann entropy, trace of minus rho log rho. So this time derivative will vanish. Okay. So there, if you start in a state with some given amount of entanglement, that state will not become any more entangled over time. So if we want to talk about the emergence of a second law and irreversibility, we can't define the sort of observable entropy in this way. We need a better definition. And the proposal that we'll use comes from, well, I'm sure it goes back a long time, but we read about it in a paper by Andy Millis et al. And what they proposed is to essentially look at the average value of the part of the density matrix projected onto the diagonal components within each bin. So recall from yesterday that this D, what it would do is it would take the density matrix. Each one of these blocks corresponds to all eigenstates that have energies lying within a given bin. And what this D will do is it will kill all of the density matrix except for this traceful part. OK, so this is a better definition of entropy for us, and we'll see that it reproduces the second law. OK, now it turns out that with this simple definition, there are two kinds of entropy in the system. So one of them is a sort of classical Shannon entropy. So this term corresponds to any sort of very long-range fluctuation or very long-range correlations that you have in your system. And the more important part of the entropy is the thermodynamic contribution. This is just going to be the sum over all regions of essentially the probability of measuring a given entropy. Okay? All right. Now let me take one of these states over here, parameterized by a beta of x, and plug in. Okay. So it turns out that this part is sort of like log L. That's how it will scale. This part scales as L to the D, so only the thermodynamic entropy wins in the extensive in the thermodynamic limit. Okay, so this S of t, we can approximate it as, in this limit, it's a sum over all regions of S of beta of x. The rate of change of the entropy is just given by ds d beta partial t beta, which was d Okay. Now if we take the continuum limit and massage this equation a little bit, we arrive at the integral over space of beta delta. And if you go back and you recall my Fokker-Planck equation, this is actually nothing but this equation. Okay. So what's the sort of punchline of all of this? So this expression, first you can integrate by parts. This is non-negative, and it's a local expression. So we have a local second law of thermodynamics. Okay? The entropy production in this system arises entirely at leading order from the production of additional thermodynamic entropy. And furthermore, the thermodynamic entropy in the system, which we computed semi-microscopically, is exactly what it has to be to be compatible with sort of Landau's phenomenological theory of hydro. So typically the way that people would think about sort of fluid dynamics would be that you would say that, okay, I write down some hydrodynamic equation compatible with symmetries. That hydrodynamic equation, I then check the compatibility of that hydrodynamic equation with the local second law of thermodynamics. Okay? And in particular, there's a specific prediction for how much entropy is produced on a given flow. And what this manipulation shows you with a bit of additional work is that we sort of microscopically have computed that entropy production, and it agrees with the historical prediction. All right, so let me stop there.